Hi there, Mr. Sutton here, bringing you the BC Calculus 8.5 Extra Practice number 2 solutions on polar functions, slope and basic area. For this problem, we need to find the slope of the line tangent to the graph at these indicated points here. So basically, we need to come up with an expression for dy over dx, but to do that, we need to express this parametrically and then figure out x prime and y prime. So let's start by getting just, how about x and y of theta to begin with? So x of theta, that's going to be r times the cosine of theta. So this -1 plus sine of theta times cosine of theta. And I'm going to simplify this a little bit before I take the derivative. So if I distribute this cosine, I've got negative cosine of theta plus sine of theta cosine of theta. And this sine cosine of theta, well, 2 sine cosine is really sine of 2 theta. So this is going to be 1/2 sine of 2 theta. Now taking the derivative of this, derivative of negative cosine is going to be positive sine of x. And derivative of 1/2 sine of 2 theta using the chain rule, that's going to be 1/2 cosine of 2 theta times 2. So the 1/2 gets canceled. So we just end up with cosine of 2 theta. Next, I'm going to write an equation for y of theta in order to get y prime. So that's going to be r times the sine of theta. So -1 plus sine of theta times sine of theta. And then distributing that sine out, we've got negative sine of theta plus sine squared of theta. And now I'll go ahead and take the derivative of this. So this is going to be negative cosine of theta plus 2 sine of theta times, we have to multiply by the derivative of the inner function sine, so times cosine of theta. So we had a little bit of a chain rule going on there. And of course, I can't resist the temptation to simplify this second term to just sine of 2 theta. All right, so I've got sine of 2 theta minus cosine of theta. There we go. I just wrote it in a different order. And now I can write the dy over dx formula. So that's going to be y prime of theta over x prime of theta. So sine of 2 theta minus cosine of theta over this one up here, sine of theta plus 2 cosine of theta. And now I'm just going to plug in 0 and pi. So let me plug in 0 first for all the thetas. So if I plug in 0 for all those thetas, let's see what this simplifies to. Sine of basically 0 is just going to end up being 0. Cosine of 0 is 1, so this is -1 up top. Down here, sine of 0 is 0. This is essentially cosine of 0, which is 1. So we end up with -1 over 1, which is just going to be -1 rather. And now we're plugging in pi. So plugging pi into all this stuff, well, sine of 2 pi is 0. Cosine of pi is -1, but it's already negative, so that's +1 up top. Down below, sine of theta is going to be 0. Cosine of 2 theta is going to be 1. So I again have a 1 over 1 kind of situation, only this time I've got a +1 up top. So this comes up to a +1 overall. On this problem, I'm trying to find the slope of the line tangent to the graph of this polar curve at theta equals pi and also 3 pi over 2. So it's really kind of two different problems. So I need to get basically an expression for dy over dx. But that's going to require me to get y prime over x prime of theta, which means basically I need to express this parametrically. So let me come up with equations for x of theta and y of theta, and then I'll get the derivatives, and then I can do dy over dx. So for x of theta, that's going to be r times cosine of theta. So distributing this 3, we've got 3 minus 3 cosine of theta times cosine of theta. So r cosine of theta. And then I'm going to simplify this before I take the derivative. So that's 3 cosine of theta minus 3 cosine squared of theta. Taking the derivative now, that's going to be -3 sine of theta. And for this next one, I'm going to need the chain rule. The outer function is squaring. The inner function is cosine. So I've got -6 cosine of theta times the derivative of cosine, which is negative sine, so actually this becomes a +6 cosine of theta sine of theta. And I'm going to simplify this second one here using the identity that 2 sine cosine is the same as sine of 2 theta. So this is actually going to be 3 sine of 2 theta. which I didn't have to do, but it's just going to make things a little bit easier down the road when I have to plug things in. All right, for my next trick here, we're going to come up with y of theta, which is going to be this same 3 minus 3 cosine of theta expression, but now we're going to multiply it by sine of theta. It's going to be r sine of theta. Simplifying this, I can write 3 sine of theta minus 3 sine of theta cosine of theta. And this second one I'm going to simplify to 3 halves sine of 2 theta, again using that double angle identity. Let me take the derivative now. This is going to be 3 cosine of theta. And then we're going to be subtracting, let's see here, using the chain rule, this is going to be 3 cosine of 2 theta. It would have been 3 halves cosine of 2 theta, but we have to multiply by that inner derivative of 2, so that cancels out this 2 here. Okay, at this time, we're going to do dy over dx evaluated at pi. So this is going to be y prime of pi over x prime of pi. Y prime of pi, we're going to be doing this stuff here. This is 3 cosine of theta minus 3 cosine of 2 theta. And we're also going to be dividing by this x prime stuff. Now, I just took the liberty of canceling out all these 3's, since everything is going to have a coefficient of 3. I just canceled all of those out. So I'm going to write out this numerator now as just cosine of theta minus cosine of 2 theta. And I'm going to write out this denominator as negative sine of theta plus sine of 2 theta. So these all had 3's, but again, I canceled all of those out. Okay, well, cosine of theta, that's going to be negative 1, and cosine of 2 theta is 1, but we're subtracting that. So negative 1 minus 1 gives us negative 2 in the numerator. In the denominator, sine of theta is 0, sine of 2 theta is 0, so that's all 0 down there. So it turns out that the derivative at pi does not exist. Well, that's disappointing. All right, well, let's do 3 pi over 2. So same setup as before, only this time I'm plugging 3 pi over 2 into all of those expressions. So cosine of 3 pi over 2, well, that's going to be 0. And this is going to be, let's see, these cancel. This ends up being cosine of 3 pi, which is negative 1, but we're negating that, so it's actually positive 1 up there. So we have 0 plus 1. And down here we've got, let's see, this is sine of 3 pi over 2, which is negative 1, but we're negating that. So that's positive 1. And over here, this is really sine of 3 pi, which is 0. So we have 1 plus 0, which is 1. So grand total of 1 for that one. On this problem, I want to find the area inside the convex limacon r equals 4 plus 2 cosine of theta. So this is a grapher problem. I'm going to start by graphing this in polar mode just to see what I'm looking at. So here I am on my grapher. I'm going to mode just to make sure this is in polar mode. And now let me go to y equals and actually graph this out. So this is r equals now 4 plus 2 cosine of theta. And the theta button is just the x button here. All right, let me check my window. Looks like I'm graphing from theta equals 0 to theta equals 2 pi. Let's see if that takes me all the way around. Zoom fit, zoom 0. And so this is what I'm looking at. And it looks like, let me just double check to make sure I'm only going around once when I go from 0 to 2 pi. So to do that, I can go into y equals and go over to this thing here. And I'm just going to click enter a couple times until I get this little circle-y looking thing. Now let me do zoom 0, zoom fit. So we go around, let's see here, one time, and that's it. If we went around another time, we would see the ball going around again. So 0 to 2 pi just takes us around once, which is good to know. All right, so in order to find the area, I'm going to use my formula of the area equals the integral from a to b of 1/2 r squared d theta. And again, there's my picture. So I've decided that going from 0 to 2 pi takes me all the way around this thing, gives me all the angular slices that I need. So I'm going to do integral from 0 to 2 pi, and just 1/2 times this r that they gave me up here. All that squared. And now I'm just going to do this on the calculator. So here I am back on the calculator. Let me clear that out. And let me do, let's see here. I can actually pull that 1/2 outside. There we go, 1/2. And then let me do math 9 to get my integral. We're going from 0 to 2 pi. And inside I'm just doing r squared at this point. Now, since I already stored this function as r1, I'm just going to go back, alpha trace, and that pulls up my R menu in this case because I'm still in polar mode, and R1 is where I stored that function. So let me just do R1 and then square that. And then I'll do d theta, press enter, and we end up with 56.549. For this problem, we want to find the area inside the inner loop of the limacon described here. So I'm going to start by graphing this out. Just to show you my setup, in mode, I have polar mode engaged here rather than func mode. And in y equals, it's now an r equals. And I've plugged in this r function they gave me. And I've also changed this little line over here. I arrowed over there and pressed enter twice to get a little circle sort of thing, so that when I graph this out, I can actually follow the order that things are graphed in. So let me do zoom 0, zoom fit, and let's see what this looks like. So we're starting over here, going around in the circle, and then going around a little bit more. So it's kind of interesting to note that if you're looking to find the area of this inner loop, you're not going to be able to use limits of integration that start with 0, because 0 is right here. You don't actually get to the parts of this loop that matter until later on angles. So it'd be nice to know at what angle we are actually hitting the pole. That'll help us when we set up our integral to find the area. So let me figure that out by taking this r equation here and setting it equal to 0, because at the pole you have a radius of 0. So if we say 2 sine of theta minus 1 equals 0, then if we add 1 and divide by 2, this is really sine of theta equals 1/2. And we know that that's going to be true at 30 degrees in quadrant 1 and 150 degrees in quadrant 2, or pi over 6 and 5 pi over 6. And just taking a look at these angles, this definitely looks like about 30 degrees right here. And if you go around, this looks like it's going to be 150 over here. So these are definitely the limits of integration then, if you're just looking to get this inner loop. So let's get our area now. The area formula, that's going to be integral from a to b of 1/2 r squared d theta. We've just found out that our limits of integration are going to be pi over 6 and 5 pi over 6. That gives me just this inner loop. And then we're just going to have 1/2 times, well, this r function right here. All of that squared, d theta. And now I just have to plug that in the calculator. So far I did math 9. I've got my integral from pi over 6 to 5 pi over 6. I've got a 1/2. And now to get this whole function in here without rewriting it, remember that I stored that as r1. So if I do alpha trace, that actually pulls up an r menu now, and I just select r1 from that. Don't forget to square that, and then go over here and put a little x, or actually it's going to be a theta, and then press enter. That gives us 0.544. So that is the area of that little inner loop. For this one, I want to find the area inside the dimpled limacon, r equals 3 minus 2 cosine of theta. Who comes up with these names? I don't know. But let's go ahead on the calculator and graph this out to see what a dimpled limacon looks like. So on my calculator, in mode, I've got this set for pole, for polar functions. And in y1, I've actually have an r equals this function right here. And just to make it a little easier to follow this thing and see how many times we're really going around whatever circular-ish shape gets graphed, I'm going to arrow over to this little line over here, press enter twice, and that's going to give me this little ball that I can follow to see where the function is going as I go through the different angles. Now I've got my window set from 0 to 2 pi. Let me do zoom 0 and see what this thing looks like. So we're starting over here, and this is probably pi, and there's 2 pi. And my ball's not going around again, so we go from 0 all the way to 2 pi as we go around, and things are pretty much as they appear in terms of different angles giving you different places on the graph. Okay, so we've got our dimpled limacon. I just want to find the area inside of it. If I take all the radius slices from 0 all the way through here to 2 pi, that will give me this whole area. So my area formula then, just the integral from a to b of 1/2 r squared d theta. So in this case, that's going to be the integral from 0 to 2 pi of 1/2, and then here's the r that we're squaring with the d theta after it. So let me plug all this in the calculator. Here's what all of this looks like on my calculator. So the thing that might throw you off is this R1. I just did alpha trace to pull up my R menu, because remember, that's where I stored this 3 minus 2 cosine of theta function in R1. And now if we press enter, that comes out to 34.558. On this problem, I'm trying to find the area inside just one petal of the 4 petaled rows r equals cosine of 2 theta. Let's go on the grapher and see what this beautiful rose looks like. So on the graphing calculator, I went into mode and changed myself over to polar mode so that I can graph these the way they're supposed to be graphed. Then if I go to y1, or y equals rather, I've entered cosine of 2 theta, and theta is just the x button now, in my R1. Now to follow what's really going on, I'm going to arrow over to this line over here, press enter twice, and I have this little ball-shaped thing that's going to basically follow my function around as I go through the angles. Which angles am I going through? Well, I'm going to start at an angle of 0, that's my theta min, and I'm going to go all the way to 2 pi and see what that draws for me. So let me do zoom 0, zoom fit, and let's follow the bouncing ball. So there we go. We're going kind of all over the place. So we're starting right here. Let me just do zoom 0 again and see if I can make it draw this again. So we're starting right there, and we're going all the way around, whole bunch of figure skating going on, and we're ending there. So it'd be nice to find out, I mean, this is going to be the angle 0 right here. That's where we started. It'd be nice to find out what this angle is here where we're hitting the pole. And then I'll probably have the symmetrical angle down here so that that could tell me which angles I have to use for my limits of integration to get this area. Okay then, so let's see where this angle, or this r actually, has a value of 0. Because when you're at the pole, the radius r equals 0. So we've got cosine of 2 theta equals 0. Cosine of an angle is going to be 0 in general at pi over 2, 3 pi over 2, things like that. And now if I go ahead and just divide everything by 2 to solve for theta, I see that this angle right here is actually going to be pi over 4, and then this other angle right next to it is going to be, well, let's see, 3 pi over 4. Okay. Although actually that's not correct. It's not going to be this angle. It's going to be another angle somewhere else. These are kind of weird, the directions that we get graphed in, because some of these are going to end up being negative radii. So when you graph 3 pi over 4, you're actually going, I believe that's actually this angle down here. Anyway, we know for certain that this first piece of the petal is pi over 4. So that means that this other one down here is going to be negative pi over 4. So our right petal goes from negative pi over 4 to pi over 4. So to find the area, using my area formula, which again is the integral from a to b of 1/2 r squared d theta, I'm just going to go from negative pi over 4 to pi over 4 with 1/2, and the r squared is just going to be cosine of 2 pi, that whole thing squared. Now I just go on the calculator and make that happen. So here's what this looks like on the calculator. So I've got my negative pi over 4 to pi over 4 limits of integration. I have 1/2, and I was a little bit lazy since I stored cosine of 2 theta as r1 in my r equals, my y equals. I just did alpha trace and pulled r1 off my menu. Just don't forget to square it. And we have a theta there. Press enter, and that's 0.393. For this free response problem, on which I can use a calculator, we have a polar curve given by this r of theta function between 0 and 2 pi, and our first task is to find the area in the second quadrant enclosed by the axes and the graph of r. Well, since we're allowed to use the grapher, let's see what this thing looks like. So to start things off on my calculator, I'm here in mode, and I've switched from func to pole mode, so that's polar mode right there. So now when I go to my y equals, I no longer have a y equals, I have an r equals, like we have up here. And specifically, I have r equals 3 pi plus sine of pi. Or not pi, theta. 3 theta plus sine of theta. Now, where did I get theta from? Well, if you press the X button, it now gives you theta. So I'm going to graph this. But before I do that, I'm going to arrow over to this line here, press Enter twice, and just get this little ball-shaped thing. This just follows the graph as it goes from one angle to another, so there aren't any surprises like going around a graph twice or something like that. And let me go to Window. So I'm graphing between theta equals 0 and 2 pi because that's what they gave me right here. So now if I do zoom 0, zoom fit, here's the graph. So we're starting at the origin, going around it looks like, and by the time you make it to 2 pi, we're all the way out here. So this is kind of like a spiral of Archimedes sort of looking thing. So with this graph, they basically want this section right here in the second quadrant. And this is going to be going from pi over 2 to pi. There's no real surprises. This thing went around in a circle 360 degrees just like we expected to. So this is definitely pi over 2 and pi. So then my area, we have an integral from pi over 2 to pi of, and now in general, the area formula, it's 1/2 r squared d theta. In this case, it's going to be 1/2 times r of theta. That's actually the name of our radius function. I could write out this whole thing, but I mean, if they already gave me a name, I'm just going to use the name. So 1/2 r of theta squared d theta, and now I'm just going to do this on the calculator. So then, let me do the integral, so math 9, and we're going from pi over 2 all the way to pi. And my integrand, I'm going to have 1/2, so let me do fancy fraction here, 1/2 times, now r I stored as r1, so if you do alpha trace here and pull up my r menu, which is kind of like my y1 menu, I'm just going to do r1, I'm going to square that, and now I'm just going to go over here, and if I press the X button, it gives me a theta. Press enter, and that all comes out to 47.513. For this part of the problem, they're telling us that between pi over 2 and pi, there is one point P on the polar curve R with an x-coordinate of -3. Okay, let it be so. Find the angle theta that corresponds to this point P, and then find the y-coordinate of point P. Sure, so we need to figure out a way of expressing the x-coordinate of this function and setting that equal to -3. Solving that will give us some theta, which we will then plug into an expression for the y value of this coordinate. So to express a polar curve in terms of x and y, for x, we can write that x of the polar curve is going to equal r times the cosine of theta. So in this case, we can say x of theta equals r of theta times cosine of theta. And then we're just going to set this equal to -3 and solve that on our grapher. Now, one thing I need to do on my grapher first is I have to go back into mode. And I went into polar mode for part A, so I'm going to go down here and change back into func mode for this part. And then let me go to y equals, clear out whatever else is in there. And I'm actually going to have to rewrite this function in here now. So let me just write this whole thing in here. I'll do that off camera. So here's what I've written in here. In y1, I actually just put the r of theta function. I'll probably need it again anyway. So that's just 3x plus sine of x because I'm back in func mode. I now get x instead of theta when I press the X button. And here in y2, I basically put r of theta, which was y1, times cosine of theta. Now, I'm going to go a little bit further, and just because I know I'm going to need it later on in this problem, in y3, I'm going to put basically r of theta times sine of theta. That's going to give me the y value of my function. So to do that, I'll do alpha trace y1, and then I'll write sine of theta, or sine of x there. So there we go. Now, all I wanted to graph in this case was y2, r of theta, cosine of theta, and I need to see where that intersects -3, so I need another one here, -3. I'm going to put that in y4. So let me deselect everything that is not -3 or the x of theta function there. So I'm going to deselect y1 and y3. Now I'm going to graph what I have here and see where it intersects. And I'm going to graph it on the interval, they said, between pi over 2 and pi. So going back to my grapher, I'm going to go to Window, and I'll do pi over 2 for my x min, and I'll do pi for my x max. And then let me just do zoom 0 and hope for the best. So the first thing that is being graphed here, this is x of theta. And the next thing that's going to get graphed is -3, the horizontal line -3. So we do see an intersection there. I'm going to do second trace, option 5, intersect, to see what that is. And let me arrow my spider over there. Press enter 1, 2, 3 times. And that gives us 2.0169 and some change. So I'm going to store that value. I'm actually going to call that Q, just so I have something to quickly refer to it as. And I'm going to store that on my calculator as well, because I know I'm going to need it again. So let me quit out of my graph, and I'm going to go to the Store button, and I'll just do alpha Q, or whatever letter you want to use. It doesn't really matter. Press enter. So now I can pull that back whenever I need to. Okay, so they also wanted to know the y-coordinate at point P. Well, I have the angle at point P. To get the y-coordinate, we can say y of theta is going to be r of theta times sine of theta. So I just need to do now y of q. So for that, I'm going to go back to my calculator. And you might remember that in my y equals, in y3, I stored basically r sine of theta. So let me quit out of there, and I'm just going to do alpha trace and pull up y3, open a parentheses, and now I'm going to do alpha q inside there, and then press enter, and that gives me 6.272. For this last part of the problem, a particle traveling along the polar curve has a position given by x of t comma y of t. Okay, we sort of already dabbled in this parametric breakdown, such that d theta over dt equals 2. They want us to find dy over dt at the instant theta equals 2 pi over 3, and then figure out what we just did. Well, if we're talking about different rates of change here, this is most likely a related rates kind of problem. So we need an equation that ties all these quantities together. Now, the important quantities here are theta and y, so we need an equation that has both of those in it, and then we'll just differentiate that with respect to time. Well, if I want to get from angles to y values, we have the formula y equals r times the sine of theta. So I can write out y of theta equals, and I'll just use this expression up here, 3 theta plus sine of theta times sine of theta. And before I take the derivative, let me actually just go ahead and distribute this. So this is going to be 3 theta sine of theta plus sine squared of theta. And at this point, I'm going to take the derivative with respect to time of all of this. So I'm treating both y and theta as functions of time. So whenever I take the derivative of those, I have to multiply them using the chain rule by a d, whatever the letter was, over t tail. So derivative of y, we're going to call that dy over dt. And now to take derivative of this product here, I'm going to use the product rule. So I'm going to end up with kind of a u prime v plus uv prime sort of structure. Let me use my box and ribbon to organize things. So I have 3 theta as one of my factors. Sine of theta is the other one. And then the derivative of 3 theta, that's going to be 3 times the derivative of theta, which is d theta over dt. Again, we have to use the chain rule whenever we differentiate one of these variables. And then for sine of theta, that's going to be cosine of theta, d theta over dt. So multiplying all that out with the ribbon, we've got 3 sine of theta, d theta over dt, plus this will be 3 theta cosine of theta, d theta over dt. And that was just the derivative of this one little product here. Now we also have to take the derivative of sine squared of theta. So that's going to be a big chain rule. We've got the outermost function, which is squaring. So that's going to be 2 times sine to the first power of theta, times the derivative of sine of theta, which is going to be cosine of theta, times the derivative of theta, which again is d theta over dt. and it doesn't look like I can combine these in any way. So what you see is what you get here. All right, at this point we have to plug in some things. Eventually they wanted us to figure out dy over dt. So that means we have to plug things in for theta and d theta over dt. And it looks like that's all that we have to plug in for. So we're going to have 3 times the sine of, they said theta was 2 pi over 3. And they said d theta over dt was 2. Plus 3 times, again, 2 pi over 3. And cosine of 2 pi over 3 times 2. Plus 2 times sine of 2 pi over 3 cosine of pi over 3. And actually, just to back up a little bit, I pulled a little bit of trigonometric trickery here, because 2 sine of theta cosine of theta, that's really the same as sine of 2 theta. So I can rewrite all of this as just the sine of 2 times 2 pi over 3. Not sure I really needed to do that, but hey, it happened. And then we have d theta over dt, which again was 2. Since I've got all constants, I actually could just stop here and leave it like this and then explain what I just did. But let's go ahead and simplify. I mean, why not? And actually, come to think of it, this is a calculator problem, so hey, I'm just going to plug this in the calculator. And I'm going to do that all off camera. So it took me the better part of a minute or two, but I wrote all of this out on the calculator, making generous use of fancy fraction mode. And this is kind of the tail end of all that. So just pressing enter and hoping for the best, I get negative 2.819, which is what all that comes out to. So what does this actually mean? Well, what this means is that the y value is changing at a rate of negative 2.819, or you could say the y value is decreasing at a rate of 2.819, which is what I said here.